Hey physics students, welcome to another edition of Rapid Review for Honors Physics. Today's episode is about analyzing collisions in 2 dimensions. Let's get right down to it. You remember P equals mv, and that these are vectors. We're going to be talking a lot about the vector nature of collisions, of momentum. So if no external forces act on the system, then momentum is conserved. We know that. I will emphasize this applies to the entire system, not to any one particular object within the system. Because it's a vector, we can analyze separately in x and y dimensions. This is going to be very powerful because we can use everything we know about vector math to do that. And let's remember too that momentum is a vector sum, right? So plus and minus matter if you're in one dimension, and then if you're in more than one dimension, you have to be careful to be using vector math and not just magnitudes. We'll see more about that soon. An example might be a ball progresses to hit another ball labeled number 11. I got this problem from my favorite textbook. I am not paid to promote this book, but I really like it. This is John Coley, Physics, 6th edition. So this problem comes right out of there. There is a solution complete in the textbook. Also, I will show a complete solution later, but I'll just jump to an answer here where we're supposed to find out the speed of each ball, and I calculated that to be 2.1 meters per second. We're going to see why that's interesting and why that result may surprise some people. I'll also comment here that the question is speed. We're looking for speed. And remember, speed is just the magnitude part of velocity. So that's where we're headed with this. You'll find the detailed solution later, but let's jump into a more complicated one. I got this from a PhET simulator. I will link to the simulator in the comments. PhET makes all kinds of good simulators. I'll be recommending some other ones in some other videos too. This one is particularly good because you can do an arbitrary 2-dimensional collision using 2 pucks with no friction. What's great about simulations sometimes is you can do things that you can't do in real life. Usually I like to prove my physics claims in real-life experiments. It's very hard to do it for a 2D collision because you need a frictionless collision. You need things moving with no friction. It's very hard to get rid of friction in a collision. So here I'm going to use the simulator and trust that it knows what it's doing. We set up some initial conditions, and there's a question asked, what is the resulting velocity? Give me the speed and direction of ball number 2. So we know the initial conditions, we know after the collision is given, and we have to figure out what's going on. We'll point out the angles were not given in this problem. So the magnitudes were given, but the angles, if you want to do this problem, you have to actually measure it right off of the screen. I did this with a projector, and I measured the angle with a protractor. Okay, so the approach to solving a problem like this is you find the momentum for each puck, then you conserve momentum, first in the x direction, then separately in the y, and then you recombine the components into the resultant. You'll notice this recipe is the same one we've used for other vector arithmetic. Projectiles comes to mind, where you separate things into their x and y components, solve x, solve y, put them back together again. That's what we're doing here. Finding the components first, x and y for each puck, then conserving momentum separately in x and y. Okay? Later I'll give you a complete solution to this problem, but I just want to mention now that you know the procedure, that this is a bookkeeping challenge. There's no one particularly difficult calculation you need to make, but you have to keep track of, I'm going to switch colors just to be a little more visible here. You know, are we talking about a momentum vector or a velocity vector? Are we talking about the x component or the y component, or the total magnitude of the vector? What are we talking about anyway? And before and after the collision, and are we talking about puck 1 and puck 2? If you do the math, it looks like there's like 24 different kinds of things you can calculate in this problem. It's a lot. So I do want to comment that the word total, I should stay in red here. I'm going to stay in red. The word total, I prefer to use the word magnitude. I don't like saying total momentum because it almost implies you're adding components together without using vector math. And if it's not obvious to you, remember that the magnitude of P is not the same as the magnitude of the x component plus the magnitude of the y component. You can see it easily here in this picture on the right side, and if you think about displacement vectors, you know, it's pretty obvious that that statement is true, but it applies to any vector that you're working with in 2 dimensions. Okay? You can't just add magnitudes. You have to do vector addition, which involves steps that you've learned already. By the way, if you don't remember those steps or are not like 100% confident in the skill of breaking a vector down into its components, or recombining it back into its resultant vector starting from components. If you're not familiar with those operations, go practice that, because you're going to need that skill for this and for future things you're going to continue doing in physics. Well, all right, I'm going to skip a bunch of stuff that we probably won't have time for, but I'm going to go back to the textbook question and show you my solution. If you want to read it, as usual, I'm not going to read it all. If you want to freeze the frame and look at it, you're welcome. If you do so, I would like to emphasize that I start out my analysis using referring to vectors, VA, velocity A, and velocity B. Later, from context, it should be evident to you that I'm beginning to talk about speed. If it's not obvious, I've put those green marks in there so you can see where I switched. I left the usual like arrowhead over the V and the usual magnitude signs. I left them out of the calculations, thinking it would probably be obvious from context which one I was talking about, and mostly because I didn't want to clutter up the page. I have to make a comment, though, about the final speeds here. If you look and see what the final speeds are, you'll see that, and yes, this is the correct answer, the final speeds are each 2.1 meters per second, okay? And some people will notice, wait a minute, you told me that the first speed in this problem was 3. That was given, right? That was given. That was the momentum of the system actually was 3 times the mass of A, right? But some students will look at the solution and say, something's wrong here because I see that you started out with 3 times the mass of A and you ended up with 4.2 times the mass of A. How did you do that? Did you get something for free? Something's wrong. And I would say to that student, be careful. Remember that you can't just take magnitudes of vectors and add them. In this case, in particular, you can't calculate the system momentum by adding the magnitudes of A and B momentums. If you take A and B magnitudes, or if you take A and B vectors and add them together, you will find that you get the answer you were expecting. All right. Finally, there's a solution here to the problem that was from the simulator. Again, I won't read everything. This is a solution that my students and I developed in a classroom. Realistically, this could take 20 or 30 minutes to do a problem like this because of all that bookkeeping. But briefly, what we did is we started out with the initial conditions. We measured our angles just from the picture, and we got a bunch of information that allowed us to get to the system momentum. So this was part 1 here. This was part 2. And then we went over this way, and we found that conserving momentum, we should have the same momentum after the collision, which was our heading there, end, right? And we used that information to solve the algebra problem to find the components of the system at the end. So this was the answer we were seeking. We were even fancy enough to convert that back into a magnitude and a direction. We had it both in terms of a magnitude and direction and in terms of its components. It looks like it was 0.59 meters per second at minus 82 degrees, which means 82 degrees below the horizontal. I think that is plenty. Here's the answer that the simulator gave us. It's the same as what we calculated. Okay, that is enough about conservation of momentum in 2 dimensions. Join us next time for another episode.